I have two different computers going, so I have the chat and everybody's video up on one computer, so I can see you if you choose to have your video on. If you don't, that's obviously totally fine. But if you want to throw anything in the chat while we're going, that's a great way to ask questions. The other, I guess, procedural thing here at the outset, if you have, no, I don't have it. If you have that note handout that I've emailed out a couple times, if you have that printed out with you, that's great. It will save you some writing. If you don't, that's no big deal. You'll just have a little bit of extra writing to do, sketching some diagrams and stuff like that. So if you have the note sheet, great. Otherwise, get ready to work your pencil a little faster. So before we start, let me just present so that y'all can see. So just a quick few notes of what's happening this week in thermo. So this is from Moodle. I should just make some of this stuff live now, but I will right after this. So there's obviously this lecture. If you want to get the note outline, that's right here, the week 3 note outline. There are going to be 2 different videos. One that is a little bit long. I don't know, I think it's like 25 minutes or something, 20-25 minutes, on thermodynamic reversibility. So that's a topic we're going to just briefly touch on today. That video will dive a little bit more in depth on it. It's a topic that we'll kind of keep coming back to, but I think it's a fairly important one. So make sure you watch that video, take good notes on it. The second video, this one here, thermodynamic machinery. That's just kind of we're going to be talking about different pieces of equipment and machines. So that just goes over, it's a relatively short one. You don't have to take any notes on that, but that just kind of goes through and hopefully will get you familiarized with what some of this stuff that we're going to be talking about, like a compressor and a turbine and a pump, what some of that looks like in the real world. So that's a relatively short one. And then that's a PowerPoint. So I have some PowerPoint slides if you want to pull those up. It has pictures and stuff in that. The last thing that's going to be for next week, there will be another quiz next week. It will run basically the same as what our first quiz did, where it's an online quiz that I think this one especially will probably have, Moodle will spit out a grade, but it won't be super useful. So I don't know. I will see how good I can make the Moodle automatic grading. But I'll for sure go back and regrade it by hand myself. So whenever you get a grade for that, that'll be next week. So you don't have to worry about that until next week, Tuesday. So I think that's all the stuff coming up today in thermo. Just a reminder of what should be done today. There should be a homework assignment and this participation number 2. So both of those should be done kind of by the end of today. All right. Okay, so we're going to dive in today with an example problem, and that will hopefully prompt some thought and discussion about specifically about energy balances and what we've been talking about with these. So we're going to do an energy balance on a nozzle. So if you bring out your printed out sheet of notes, this is the first question on that. And if you bring that out, what we have happening here is we have a nozzle, and it's steam's coming in one side and it's shooting out the other. So we know from a mass balance, obviously, what comes in one side has to be leaving out the other side. And we know from an energy balance that the energy coming in one side has to be the same as that's coming out the other side, right? Those energies have to match up because of conservation of energy. So we know this system has to obey conservation of mass, conservation of energy. What we have happening, we have an initial velocity of 50 meters per second. That's pretty fast. I can't remember off the top of my head. You all have computers. Is that like 120 miles per hour or something like that? I don't know. I think it's times like 2.2 or something like that to get to miles per hour. But somebody can check me on that. So it's coming in fast, but not crazy fast, 100 miles an hour. It's coming in, the initial pressure is 600 kilopascal. So that's like 6 times atmospheric pressure. So again, it's not low pressure, but it's not crazy. If any of you have ever seen like the scuba tanks, a scuba tank, usually the pressures on those are, what are they? I think around like 2,500 kilopascal. So maybe 5 times, maybe more than that. I'm trying to remember off the top of my head. I think they're actually more than that. So, right, it's high pressure, but it's not like as high as a scuba tank. Not really that close. And it's at 200 degrees Celsius. So it's steam. If we look up what the enthalpy is for that, right, we're looking up 600 kPa and 200 degrees C. Okay, so if we go over to our steam tables and look that up, we would go to the, well, we could convince ourselves that it is actually a gas phase. So here we are in the saturated water pressure. So these are the saturated tables. If we find 600 kilopascal, then this temperature right there, 158.85, that's the boiling point. So this 158.85, that's the boiling point of water at 600 kilopascal. We're at 200, we're above that, so we're steam. Okay, so we can go to the steam section, superheated water vapor. Okay, then so we can erase some of this scribbling from before. So we're going to be right here at 200 C and 600 kilopascal. So our enthalpy is right there, 2850.12. Okay. We can do an energy balance to figure out what the exit velocity is going to be. So we'll just skip ahead to the next slide. So our energy balance, if we want to determine the velocity, we can start with our general energy balance. Delta H dot plus delta E dot K plus equals Q minus W. And our we're basically going to go through and see what which terms survive this. Right. So if we look at this delta H, delta H is basically always going to be a part of our energy balances, right? Because it's the heat energy of mass coming in and out of our system. So we have steam coming in and out of our system. We have a delta H. Kinetic energy, we're going to have kinetic energy changes because that's the point of a nozzle. And generally, these are going to be the only systems where we really have major kinetic energy changes. If we have a different kind of system like a turbine, We would expect kinetic energy changes, but they're going to be small relative to the other types of energy in the system. So typically, as a first approximation, we can ignore them. If you're actually doing like detailed turbine design for a power plant, then you're going to need to take those into consideration. But kind of for our first pass, we can typically ignore them unless it's a system like a nozzle where it's specifically designed to give you a kinetic energy change, or you're told, like in the problem, the initial velocity is this and the final velocity is this, something like that. So unless you're told something specifically about velocities, or it's something like a nozzle that's designed to give a kinetic energy change, we would ignore that. We have a nozzle, so we can't ignore that. Potential energy change, kind of the same thing, unless we're specifically told stuff about potential energy change, it's typically fairly small. In this case, right, that's going to be the difference in kind of the inlet and the outlet height. That's probably going to be a fairly small value, so that will be a fairly small energy. So this is about equal to 0. For heat transfer, so there is going to be, right, you're going to have steam coming in this side here, and it's going at like 100 miles an hour. So it's not going to be inside of the system for more than a fraction of a second. So in this case, there's just not a lot of time for any heat to be exchanged. Like, even if this nozzle is hot, even if the nozzle is hot and it is exchanging heat with the surroundings, like it is radiating heat or something like that, it's going to be fairly small because the stuff is just screaming through, right? It's going through so fast. So Q is about 0. And then work is only going to be, this is shaft work, so it's only going to be present if we have like moving mechanical parts. So that's going to be exactly equal to 0. So potential energy, not exactly 0, but it will be small. Heat transfer, not exactly 0, but it will be small. So the energy balance that we get is delta H plus delta E K is equal to 0. Or we could write that right, we can kind of expand delta H as our enthalpy out minus our enthalpy in times the mass flow rate plus, again, mass flow rate times 1/2. And I'll try to make this bold because this is V2 squared minus 1/2 V1 squared. So that would be, this 0 equals. So we could do either of these. This would be our kind of expanded version here. Okay, so what we know so far, we are given, if we go back to the problem, we're given the initial velocity. We found the initial enthalpy. So we have 2 of our 5 variables. We can just divide by, we can divide both sides by m dot, and that will actually just fall out of the equation because we have a 0 on this side. So we have this, we have this. We need one of the either final velocity or final enthalpy. If we go back, we can actually find the final enthalpy because we have 2, we have both pressure and quality. So a quality of 0, right? This means that it's a saturated liquid. So what that means, it's liquid water, but it's exactly at the boiling point. So it's, in this case, 100 kilopascal is about atmospheric pressure. So it's liquid water at 100 Celsius, at least about 100 Celsius. If you look that up in your tables, that should be 4 417.44 or thereabouts kilojoules per kilogram. So then we have all of the numbers that we need. So we can write 0 equals 417.44 kilojoules per kilogram minus 2850.12 kilojoules per kilogram plus, we can just pull the 1/2 out in front. And then this is going to be velocity 2 squared minus 50 meters per second squared. So we run up into a little bit of a unit conundrum because we have on one side and one set of numbers we have kilojoules per kilogram. On the other one we have meters per second meters squared per second squared. But if we remember, 1 meter squared per second squared equals 1 joule. So the unit conversion is actually, or 1 joule per kilogram. So the unit conversion is actually fairly straightforward. 1 kilojoule per kilogram is 1,000 meters squared per second squared. So we write, if we move stuff and solve for V2, we'd write 0 equals 417.44 minus 2850.12 times 1,000 plus 1/2 V2 squared minus 50 squared. And then this would all have units of joules per kilogram, or I guess it may be easier for this. This would be meters squared per second squared. And we're going to be working in those units because we're going to be looking for the velocity. So I don't have a calculator in front of me to plug all this stuff in, but it's fairly straightforward once you do. And you can solve for the final velocity. V2 would be equal to about 2,206 meters per second, or about 5,000 miles per hour. Okay, so we'll stop there for a second. How does that feel to everybody?
Seems fast.
Yeah, it feels a bit unrealistic, like we made an error or something.
Okay, so let's go back to this part. We have, what do we have happening? We have steam. So this is at kind of a moderate pressure and temperature, nothing crazy. And it's going in at what, like 120 mph, something like that. Somebody can check me on that if you like go to Google and do the conversion, 50 meters per second to miles per hour. And it's coming out at 5,000 miles per hour as liquid water. Okay, so you all know that that's stupid, right? This is wrong. This is completely wrong. We all know that. So there's no way that you have a gas flowing in one side of a nozzle at about 100 miles per hour, and it's coming out as just a jet of pure water at 5,000 miles per hour. So what's actually wrong with the is it our calculation? Right? Did we do our algebra wrong? I can promise you that we didn't do our energy balance wrong. So this part, if I just get a different color here, right? This part is all correct. All of these assumptions, those are all correct. When we plugged in actual values, when we looked up values in the steam tables, those are the correct values. This was the correct equation. We did our algebra right. We got the right answer, but it's crazy. So what actually happened that was wrong? Because obviously something must be pretty wrong, because this is obviously physically unrealistic.
Would it be the number for H2 we got from the table? Because it's kind of low compared to the H1 value going in.
So you're right. It is low compared to the H1 value going in. And that's what gives us, you're right, Nolan. That's what gives us the wacky answer. The value itself is correct, though. So it's correct for a saturated liquid at 100 kilopascal. So what we have to remember, though, is, right, if we go to sorry, if we go to if we go back to what we've actually done in the problem, we've done a first law of thermodynamics calculation. So we've looked only at one of the two laws of thermodynamics. Remember, there are two laws. So the first one is that we are able to change thermal energy to mechanical energy, and that's what we did here. We took this amount of thermal energy, 2850. We took this amount of thermal energy from our system, and we converted it to mechanical energy, right? The thermal energy went down, and the mechanical energy here went up. So what we have to do is remember that it's not just one law of thermodynamics, there are two. So the first law of thermo is that we can do energy balances. The second law of thermo is that we have to be a little careful with our energy balances because heat only flows one direction. So it's a little bit hard to tell that just from thinking about this problem, but this is equivalent to right, us putting a hot thing and a cold thing next to each other, and the hot thing getting hotter and the cold thing getting colder. Those are actually, that's what's happening essentially in this system. So this first law of thermo let me get just a blank document. So the first law allows us to do energy balances. Right, this is kind of the definition that we've typically been using. Heat can't flow cold to hot spontaneously. So the first law tells us that we can do energy balances. The second law sets limits on what we can do, on how much energy we can change from thermal energy into mechanical energy. So there's a video that you're going to watch on thermodynamic reversibility that goes into this in a lot more detail. So I'm not going to say too much about it, and we're not going to take too many notes on this right now. But the interesting thing is this gives us an equality, right, where we can say like our energy balance, one side is equal to the other side of the equation. The second law gives us an inequality. So it's going to say we can't do, this is going to be the law that says we can't do better than this. This is the best that we could do. The property, and again, I'm not going to go into too much detail here because we'll do more of this later, but the basic law is that mathematically the second law is that the sum of this new variable we'll call S exit, minus the sum of S in, the sum over the entire universe, is greater than or equal to 0. So this is the mathematical statement of exactly this. Heat can't flow spontaneously from cold to hot. If heat did go from cold to hot, that would mean that this variable S, right, what this is saying is that S must get bigger or at least stay the same. It can't get smaller. So S must increase. And it's a sum over the universe because it means you have to look at the entire system because if you look at just one little specific spot, S in that little specific spot can decrease. But if it decreases in one place, it must be increasing by a bigger amount somewhere else, or at least the same amount. So S is the thermodynamic variable, which we'll call entropy. That's supposed to be a letter N. That's a pretty bad one. Entropy. So we give entropy. It's going to be the key property, which gives us information about the second law of thermo. And it's going to be our check of kind of can the process happen or can it not happen? It can happen if S is going up from, say, like, the inlet to the outlet. If we go back to our nozzle, okay, I missed, apparently I didn't save the latest version of this. If we go back to our nozzle and look at what the entropy here is and the entropy here, right, S is just a value that we can look up in the table. You may have heard people have kind of more philosophical discussions of entropy. We'll do maybe some of that, I guess, later in the semester, but we're going to save some of that. Right, it's a variable, it's a property like enthalpy, like internal energy, that we can just measure for our system, right? When we look up values in our tables, if I go back to one of our thermodynamic tables, if I want to find the entropy of our inlet, right, I would find, again, right here at 200 degrees C, here at 600 kilopascal, this is where we found the enthalpy, and this is where we would find the entropy, right? It's this value S. The units are kilojoules per kilogram Kelvin. So the value of the entropy is 6.9665. So this would be 6.9665 kilojoules per kilogram Kelvin. And if we wanted to find the entropy of the outlet, so that's 100 kPa and 0 quality, could go up to our tables. Okay, we would find here 100 kilopascal. 0 quality means, right, that we're looking at the saturated liquid columns. So this is where we got our enthalpy, 417.44. And this would be our entropy, 1.3025. Okay, so we look them up. We look up entropy the exact same way as we look up specific volume or enthalpy. We look all of these things up the exact same in our tables. It's just the column S. So I forget what I just said, but it was like 1.3. Is that right? Something like that. Kilojoules per kilogram Kelvin. So if we calculate the change in entropy, right, delta S equals S2 minus S1. So that would be like 6.9 minus 1.3. We'll write abouts because I'm not dealing with significant digits very well here, but you get the point. So this would be a negative 5.6 kilojoules per kilogram Kelvin. So what we could say for why this system is implausible, right? Not implausible. Why this system is impossible. Why the nozzle that we did our calculations for. It wasn't because we did our energy balance wrong. It wasn't because we made math mistakes. It's fundamentally impossible because entropy decreased. Good call. So it should be S2 is 1.3 minus 6.9. Thank you. Good catch. Thanks, Ellie. So if we go back, the delta always means out minus in. So our outlet here is 1.3 and our inlet here was 6.9. I guess it would round to 7, but close enough. So our kind of a more rigorous explanation for why, right, our explanation in part B was, does the exit velocity seem plausible? Of course it does not, right? We all agreed that, or at least I hope you agreed with that. A rigorous explanation for why would be because, so something like, yes, the nozzle is impossible because it violates because it violates the second law of thermodynamics. So that would be, yeah, like I said, that would be a more rigorous way of saying that, yes, this doesn't work. Right, delta S is less than 0. So that's, again, our mathematical reason why we're violating the second law of thermodynamics, because the change in entropy of our system is less than 0. So a natural question which we can ask then, and one which we'll ask quite a bit, is, okay, if what we said from our second law, so the mathematical definition of our second law is this, that entropy has to increase, or at least be 0, or at best be 0. So kind of the logical extension of this is we can use the second law to define a best possible nozzle, or really any best possible, like best possible case process. And we can do that by saying, okay, so the best possible case is if delta S is equal to 0. And we can use that as our benchmark for how a system could actually perform. Again, it's not an actual physically realizable case because it's the best possible case. We're never going to actually be able to get there. We'll talk kind of again in the semester about this. We'll talk quite a bit about it and say how close can we actually get. You know, sometimes we're maybe only 70% of the way there. Maybe we're 90% of the way there. We're never going to get 100% of the way there, but we can get close, and it's a good benchmark because it's right. It's kind of the universal speed limit. Like this is the best that we could do, and we can see how close we can get to that maximum. So we can do that by looking at at a process where delta S is equal to 0, at least in this case. Really what we're doing is looking at a process here, and I'll just write watch video 1. So I'm gonna talk quite a bit in detail about what exactly this word means. It doesn't mean, in the context of thermodynamics, it doesn't mean exactly what we mean in like normal everyday language. It has a very precise meaning. It's a term. The term reversible is going to mean something very specific in this class. So we have to be really careful with how we use it. Kind of the easiest way is maybe reversible equals best possible. That's maybe another way, maybe the easiest way to read it. But really, I mean, it's a process that it does kind of mean what I don't know. It's hard because the definition is a little bit tricky, but it does mean a process that you could go forward and backward, and there would be no change to the universe, is kind of essentially what it means. It's something that, right, if you took something and compressed it, and then you let it expand, it would be exactly, the whole universe would be exactly the same as it was before you did that. That's like the quick 30-second definition. Again, it's something like I spend, 25 minutes talking about it in the video. So that's just kind of a teaser. Really, I mean, it's the best possible process that we could do something by. So in this case, if it's a reversible nozzle, And we'll get to exactly why, again, in this video, why this is true. But if we have a reversible nozzle, that means that delta S is exactly equal to 0. So we would still have the same inlet conditions. So this is still going to be 2850.12 kilojoules per kilogram. The inlet entropy is still going to be 6.9665 kilojoules per kilogram Kelvin. Now the difference is we can't, and I don't know why I did this, but this, you don't have that on your printout, I hope at least. I think you have temperature there as a blank instead of quality. But we don't know this, that was a vestige from copying the first part. So there shouldn't have been a quality there. If we only know if this is the best possible nozzle, we know that the steam expands in this best possible process, which we'll call reversibly, to the same final pressure, 100 kilopascal. So this is a nozzle that's shooting out into just the atmosphere, which is at 100 kilopascal. And if it's our best possible process, that means that this change, delta S equals 0. So we know that the final entropy, 6.9665, we know that final entropy because of the process that's happening. So, right, we know the inlet state because we're given 2 pieces of information, and that allows us to find these other 2. We know a single piece of information about the outlet, but now we know how we get from point 1 to point 2. We know we get there by a reversible process. So that path, you want to think about it that way, that path from getting to 1 to 2, that's what tells us this second piece of information, the path or process. So then what we have to do is find those values. So we're going to be looking up values. Okay, so those aren't correct anymore, but we are still at 100 kilopascal. So this is our pressure. And now we're looking for this pressure and our entropy, which is 6.9665. So we're going to look and try to find the state. So our saturated liquid was 1.3025. So we're higher than that. So we're not saturated liquid. Our saturated vapor is 7.39 or 7.3593. So we're actually lower than that because we're 6.9. So we're going to be somewhere between these 2 values. So we have to use the concept of quality. But we actually do know one thing. So we're going to be a vapor-liquid mixture. We're going to be at 100 kilopascal. This is our temperature, 99.62 Celsius. So if we go back, our T equals 99.62 degrees Celsius because we have a saturated vapor liquid mixture. We're going to find our entropy by S equals SF plus quality times SFG. So our entropy is 6.9665 kilojoules per kilogram Kelvin. That equals, what is it, 1.3025. Right, so this is SF up there. This column here in the middle is SFG, so we're going to use these two numbers. 1.3025, 1.3025 plus X times 6.0568. Okay, and if we go through this and we solve for quality, we would get that the quality equals 0.9351. So the best possible nozzle, we don't get, right, the one that we did in the first case, we got pure liquid water. It was at the same temperature, it was at the boiling point, but it was pure liquid water shooting out of our nozzle. Now we get basically all steam with a little, a few droplets of water, a few droplets of liquid water. We then would have to go back and find H2. And H2 is going to be equal to HF plus, now this quality, 0.9351 times HFG. I'm not going to do that here, but that's 2529 kilojoules per kilogram. Okay, so our final temperature is going to be 99.62. Our final enthalpy is going to be 2529. So just one last quick thing before we end here. The energy balance that we did the first time is still correct. So we do the exact same energy balance. We just, in the first case, we converted more energy than was possible from thermal energy into mechanical energy. We broke the second law. In this case, we're doing the best possible case, where we're obeying the second law, but we're doing the best that we can. But we still get, right, the same energy balance. 0 equals H2 minus H1 plus 1/2 V2 squared minus V1 squared. This is just now, right, this is 2850.12 minus 2529 times 1000, and that would have units of meters squared per second squared plus 1/2 V2 squared minus 50 meters per second squared. And we could go through and we could solve for our final velocity. V2 is about 800 meters per second. So in our first case, we were able to break the second law because I just chose an outlet value, and I chose a final state that was unrealistic, that was not possible. In this case, we went through and said, okay, if we went from point 1 to point 2 in the best possible way, that best possible process, this would be the best that we could do. And then kind of the flip side of that is now then this gives us a benchmark. If we designed a real system, this gives us a benchmark by which we can evaluate our performance. So that will be, we'll talk a little bit more about how we do that and how we take real systems and kind of benchmark them to these best possible systems. But that will wait till next time. Like I said, make sure to watch the first lecture video, especially where we talk a little bit more about this thing that we call the reversible process. We'll kind of continue bringing that concept up. You'll see that come up a lot, where we talk about actually how we get from point 1 to point 2. But that's gonna become a really important concept. The homework and the quiz, I think there's one problem on the homework that's from this is chapter 7, so we jumped ahead. Energy balances are in chapter 4. Some of the second law stuff is all the way in chapter 7. So they're like energy balances. You solve them the same way, but you have to know something about how you get from point 1 to point 2, how you get from the inlet to the outlet. And that's where this concept of entropy and the second law comes into play. The homework is mostly going to be chapter 4, which is just strictly energy balance problems. The quiz will be a chapter 4 problem. So there are a couple example questions, but the quiz that we have next week is not going to be covering entropy at all. So it's just going to be just first law stuff, just an energy balance thing. So make sure you check some of the stuff that's posted on Moodle about the quiz. Hopefully that clears up any details. With that, I'm going to stop the recording.